we are studying the we're starting the new chapter about rotations. So we're right here. So for the projects, the most important meeting will be not coming when everything is important, but the second next Wednesday. The Wednesday after Thanksgiving is when everyone is assumed to conclude everything. So just do nothing, relax, accumulate force, and do everything. Well, it is what we do. So why are we going for rotations? What is interesting and important? Who is rotating? I assume that Alex will know because of his tenure at work group of Dr. Herberger. And tech support. May I ask to focus the camera on the just on the screen. So who is rotating? Any common sense? It's not correct. Electrons are rotating around what? Yes, it's most correct, classical, canonical, important answer. So if we have a humble question of predicting spectrum of hydrogen atom, we need to take into account rotations of electrons around the nucleus. But what else in the physical chemistry characterization of atoms, molecules, and materials may rotate?
Bonds?
How bonds can rotate?
They can rotate, yes.
But it's not bonded, the whole molecule can rotate. Right? Like if I get tired of the cell phone, I can throw it and it will rotate. Well, I postponed doing it. So, you know that if we have, well, the best example to keep in mind when thinking about characterization physical chemistry is diatomic molecule. It is simple enough that one can potentially do some pen and paper calculation, but it is complicated enough to represent. So there is an interatomic bond. It's a molecule, not an atom, and it also can rotate around itself. Not electrons around atoms. They are rotating so quickly that they are heavily quantized, and it's just electronic clouds, SPD orbitals. But when it is molecular rotation, they're also quantized, but it is like easier to imagine. So why rotation is important? And what like diatomic molecules is doing? It's rotating, oscillating, and there are electronic degrees of freedom. Right? So electrons in the atomic molecule can be in ground state, but one can send a laser pulse and excite it in higher states, which we will consider in the remaining time. There are oscillations, which we can very approximately consider just classically, or we can consider that it is quantized oscillator near equilibrium. And there is one project about how infrared radiation increases, pumps energy into oscillations. But in addition, it can rotate. Why all of these degrees of freedom are needed? Can one see it on experiment?
NMR?
NMR, it is next level. It is nuclear magnetic resonance, because there is a spin associated with nuclei. And the spectroscopy for NMR is in the radio frequency. But if we are going from, like in each range of electromagnetic radiation, there is a specific spectroscopy. Like UV visible is for electronic transitions, infrared for oscillations. And if one goes to long between infrared and microwave, there will be rotations. If there is a popular picture in textbooks and in Wikipedia that I want to attract your attention to. And if I behave well, if our plans will be successful in describing rotations, we will be able to predict this picture. So, have you ever seen something like this? Bird with wings. Who never saw this figure? Just you don't need to be explicit. Who has seen it once? Oh. Okay. So, would you volunteer to express what it is?
Isn't it the wavelengths of light that the rotations will absorb? So if you're shining a light through it, if they rotate, if the wavelength corresponds to a rotation, isn't that where it absorbs it?
Yes, it absorbs, rotation absorbs energy, but it's not only rotations. It's simultaneous rotations and oscillations. So the diagram here, so I have forgotten to say most important summary. Why all degrees of freedom are needed? Each degree of freedom in a molecule is quantized. But the offset of energy levels for each type of motion is on very different range. They're different by orders of magnitude. Like electronic energy offsets like 100 times bigger than nuclear motion energy offsets. Vibrational energy offsets are like 100 times smaller than frequency of oscillators. Therefore, there is a common picture that physical chemists and spectroscopists accepted even before any substantial development of quantum theory. Like, if we do have a quantum level, it will have a lot of sub-levels because there are additional degrees of freedom and it contributes to line broadening. Make sense? So like even if we look on maybe two electronic states, one ground, one excited. In fact, this excited state will consist of like 10 vibrational sublevels and 100 rotational sublevels. Therefore, it will, remember when we were speaking about density of states, we assigned some width to each level. So the background for assigning width to a level, because there are some additional degrees of freedom that we are not taking into account explicitly, just because we are lazy in the present sense. So this figure is, for diatomic molecule, we have ground state of oscillator, amount of oscillations 0, and first excited state of oscillator. But these vibrational states do have vibrational sublevels. And if we decide to irradiate this diatomic molecule by light, it will absorb energy not only at the resonant transition corresponding to vibrational frequency, but it will be able to absorb at slightly smaller and slightly larger frequencies. Because it can go from lower vibrational sublevel to higher vibrational sublevel. And opposite, from a little higher vibration sublevel here to lower vibration sublevel there. And if you take it like the pure vibrational transition will be on this diagram here, the spectrum. And these wings are simultaneous transition changing both vibrational quantum number and rotational quantum number. If our spectrophotometer will have low resolution, all the swings will merge into just one thick line with some broadening. Okay? Makes sense? So we will apply a little effort in order to be able to reproduce this figure, at least qualitatively. Okay? So it's motivation number 2. And motivation number 1 was that everyone immediately answered: rotation of electron around nuclei. Yeah, it's too early, but since the rotational levels are so close to each other, their offset is smaller than thermal energy. They all will be populated, and there will be transitions between them weighted by Boltzmann distribution. And this will give this set of transitions. Another thing that I hope to arrive to this picture sometimes on Wednesday. So if we want to describe what is happening to rotational degrees of freedom, we need to recall a concept that you were very well acquainted at a time when we spoke about multidimensional boxes. Remember, density of states or box of different dimensionality depends on aspect ratio. And when we come to a three-dimensional box of equal sides, we realize that for each range of energy, there are so many states with the same energy, or approximately the same. And this effect is called degeneracy. Same energy, many quantum states. So if one wants to predict outcome of experiments, one needs degeneracy, and we will hopefully cover the degeneracy for rotational motion. So you will see this table again. So quantum description of rotation is challenging. We do not have time to do it. Because if you take your pens and try to play with it, one can rotate it in the plane parallel to a table, right? But in addition, you can play rotations outside of the table plane, right? And if there are simultaneous rotation in all directions, it is doable. It is one of the quantum problems that can be solved with exact answer. But I need to appeal to the college to make this course 1 year long rather than half year in order to include it. In what we can afford in a given time is to consider only rotation in one plane. It will be not sufficient to give all details for real experiments, but you get a flavor and mathematical tools that will be needed to develop further for actual answer, but with additional time, each of you will be able to do three-dimensional rotations as well. So what we are going to cover right now is an approximation. It is far from describing realistic systems, because both two diatomic molecule, when it has activated rotations, and electron moving around nuclei, they perform three-dimensional rotations. So this approximation is just same as we can earlier we considered universe with only one electron, one-dimensional. Approximation just to get muscles. Now it's a maybe two-dimensional universe like everything is squeezed in z direction, and it can rotate only in x and y. And also there is an approximation that I have to do, otherwise it will be too much, that the rotational motion will be frozen. So if we are going to apply this model to electron moving around nuclei, like Bohr model, then we will need to assume that distance from electron to nuclei doesn't change. Do not tell it in public. It's from the modern use. It's already heresy. It's only a little mathematical toy to play. Important for educational growth. So if one assumes that distance from electron to nuclei is fixed, if there are like shells and orbitals, and it is squeezed in 2 dimensions, then it is what we will be doing. Very simplified. For rotation of a diatomic molecule, we will assume that there are no oscillations. There are fixed distance between nuclei in this diatomic. Fixed distance, which word would characterize it? Soft or rigid? Rigid. If it is rotate, then the word is rotor, right? Same like if you disassemble drill, you know, if you're mechanical, there is a rotor, the stuff that rotates inside the drill. So, rigid rotor. So the subject that we are covering is 2-dimensional rigid rotor. So what is shown here? If we are speaking about electron around nuclei, then here is the nuclei, here is the electron. Here is the fixed distance. Here is the trajectory or it moves. What is the independent variable? Scroll back. You all are already big experts in quantum theory. You did truly challenging homeworks, and you shouldn't underestimate your strengths. You know a lot. But from your experience and point of view, if you want to solve some quantum problem, to model something, what do you typically need?
Initial conditions.
Yes. What else? The simplest quantum problem is time-independent Schrödinger equation. Right? The wave function and quantum and eigenvalue are not known. What is known in time-independent Schrödinger equation?
Hamiltonian.
Yes. So it's words of extracurricular class, but I assume that everyone knew, right? So while starting new quantum problem, one needs a Hamiltonian. So we do need to set up a Hamiltonian for this rotational motion. And typically, well, we already know that Hamiltonian can be expressed in discrete space or in continuous space, but if we are looking to Hamiltonian as differential operator in continuous space, we need to identify independent variable. Before, when we looked at the free space box oscillator, our independent variable was Cartesian position, right? What will be independent variable for rigid rotor?
Speed at which it's rotating.
Huh?
Speed at which it's rotating.
Interesting.
Or are you looking for the angle at which it starts at?
Better.
The radius.
Radius. We already agreed. At least no one was protesting that we will consider rigid rotor. which means radius is a constant. Yeah, if it will be full size problem, of course, radius will be changing. If time will be not favorable to me, we may not have time, but it is assumed as a common knowledge. Hydrogen atom. How many quantum numbers? Principal, orbital, magnetic, spin. Right? And principal, it's when distance from center to electron is changing. Angular is when rotation happens at different speed. Magnetic is rotation only in two-dimensional projection changes, and spin up and down. No principal quantum number today. Radius is not changing. Well, let me slowly walk from continuous distance to angle. Angle was the right answer. But we are already so experienced in the Cartesian distances. So if the electron is moving, we can start measuring arc length from the origin along this curved surface, right? Let's call it lowercase l. But if the radius is fixed, then this arc length is connected to the angle. Right? Small change of arc length is radius times small change of the angle. Right? And interestingly, then if it's just a little mathematical experiment. If you look on the derivative of angle over arc length, it will be 1 over r. It looks like useless, trivial thing, but later on it will help us a lot.
Is there a pi in that equation?
Why?
I don't remember those equations. So.
I was reading jokes on the line, so do not. I probably should take it off record. So it was a jokes about like class, and the instructor asks in which units people measure angles, and the class answers in degrees. Hey, you alcoholics, degrees are for ethanol. True mathematicians measure angles in radians. About your about 2 pi radians. So we should take it off the record. But the angle, the units of angle are radians, and if it makes full rotation, then it will be 2 pi, right? But if it is small increment, it's just angle. Okay. So why we do this? Because we need Hamiltonian. We need Hamiltonian. Do you have an idea how Hamiltonian will look for this motion, or not yet? It will be not a big crime to tell. I know. It's not a secret note. You can, if you want, you can try to derive it ahead of the class. So, a little numerical experiment before we go to before we try to derive Hamiltonian. So, we do have experience in continuous lengths. Arc lengths can be independent variable. But there were voices, for example, by Alex, that angle is better. And it looks reasonable to use angle rather than arc lengths. Okay? So we have experience in derivatives over length, but we need to convert, because Hamiltonian typically consists of differential operators, derivatives over independent variable. So if you go from derivative over length to derivative over angle, we need to do this conversion. Okay? So if our wave function depends on distance and angle, but we know how to do this, how to deal with length. Can we convert this derivative into derivative over angle? What is written here? Chain. Okay. So if we do have derivative over L, we can multiply and divide by infinitesimal increment of different variable. Okay. So we can multiply and divide by increment of radius and increment of angle. Then it will be change of wave function in respect to position, and we know that it will be 0 because we agreed that we dealing with rigid rotor. And here, change of the wave function. So psi is wave function, phi is angle in respect to angle times derivative of angle in respect to arc length, which we just considered, which will be what? Yes. So here is conversion from arc length distance to angular variable. This is the simplest example of differential conversion from rectangular to curvilinear coordinates. If we would do truly hard mathematical work on three-dimensional rotation and hydrogen atom, we would practice similar ideas for more advanced three-dimensional operators, and the conversion would look somewhat more complicated. But the main idea, what we did here, it was trivial mathematically, but it is ideologically, it's really helpful. We performed conversion of differential operators from rectangular system of coordinates to curvilinear system of coordinates. Whew. What is my goal? My goal is Hamiltonian. No one objects. Okay, so one more auxiliary thing that will pop up and later will be helpful. What is angular momentum? Anyone who wants to help me?
Momentum, a spinning on.
Okay, so it's way to quantify rotational motion, right? Good enough. But quantitatively, how it is done? Is it like cross product of radius times momentum? Yes. Can you show it one second? Yes. Show what you're doing.
Just trying to get angular momentum to be
Look at his hands.
some, but then the fingers as a whole.
Radius times the curve
Oh yeah.
velocity.
So your velocity would be your knuckles, and this would be your arm, and this would
Correct. How do you call this rule?
be right angle.
It is name for highly moral people. I was exposed to environment where it was called corkscrew. If you need to open wine bottle, doing the same, right? So right hand rule or corkscrew rule. So radius, momentum, and their cross product, angular momentum. in case our vectors of radius and momentum are in xy plane, then the angular momentum will be, according to these rules, will be oriented in z direction, and there will be no other components of momentum. So angular momentum is three-dimensional vector, but in case our rotation happens in a plane, it will be vector collinear with z-axis. There will be no components for x and y angular momentum. Therefore, we select this simplification. And if the angle between radius and momentum is, I shouldn't say 90 degrees, because degrees is not our choice. Pi over 2, right angle. Then the cosine between them will be 1, and it will be z projection of angular momentum would be radius times momentum parallel to this arc length. So if we do, be careful. It's not super important, but if you decide to follow, do not slip. I'm jumping through different concepts and very little details in notation without focus. It's easy to miss them. So it is momentum parallel to arc length. It's momentum along arc length coordinate. Right? P sub L. And if we know a direction, a coordinate, and we want to express quantum operator of momentum along a specific direction, we can practice our definition of momentum. Before, when we had P x was minus I h bar d dx. If you have P sub L, it will be minus I h bar d dl. But now, I'm just skipping. We are replacing derivative over arc length onto curvilinear derivative over angle, and here is the coefficients of transformation from rectangular to curvilinear derivative, 1 over r. Right? So this one is momentum along the arc length. And this is distance from origin to our position of our whatever electron or size of our rotator. So prepare for a little wonder. Distance will cancel here. Minus bar d d sub z. This is really good luck for all of us. So we in fact, we are considering curvilinear motion. Typically, it's something like something that scares me. But here, through this trick and through the right choice of variables, of operators, we found an operator, L sub c, projection of angular momentum, that looks really simple in our choice of variables. So if our independent variable is angle, and we want to further deal with projection of angular momentum, then this operator looks similar way as regular momentum in Cartesian space, right? Just derivative over independent variable times time constant and imaginary unit. Which means probably we can use all tricks and experience that we practice for particle in the box for linear motion, with understanding that now our independent variable will be not position but angle. We see some similarities, right? Whew. What is my goal? I'll go together. It's good that we are not in the. I should also took it off the rotor. It's good that we are not in a communistic country, because if you are in the communistic country with mass media trying to do brainwash, everyone on the question, "What is our goal?" should answer, "Our goal is communism." Okay, but so what is our goal?
Hamiltonian?
Yes, Hamiltonian. So we already do have the angular momentum operator. It looks really appetizing, really easy to perceive. Now let's think on how can we formulate the Hamiltonian. Let's remember, what was the Hamiltonian for the free space?
No potential.
No potential, only kinetic energy, right? Good. Do we have potential here? Rotation it's free rotation. It doesn't change, it doesn't feel anything else. We assume that it is like diatomic molecule in vacuum or hydrogen atom in vacuum. At any angle, it will be the same motion. So it's a really good idea. Hamiltonian is expected to consist only of kinetic energy. Now, how did we express kinetic? How did we express kinetic energy in free space?
Negative h bar squared over 2m times momentum, or times the d squared dx.
It's correct and too smart for me. I'll say just p squared over 2m. Right? And here we are assuming that it is momentum along the arc length. Now, look at my hands. There will be nothing cheating. It's clean hocus pocus. Let's multiply numerator and denominator by r squared. R squared. R squared. Will the operator change mathematically? No? Good. So continuation of the hocus pocus. I didn't lie. Now, let's consider the nominator as p sub l times r squared. Did I lie? No. Now, next step. How did we recently define product of distance times momentum along this curvilinear arc length? Yes. So L sub z squared divided by 2 m r squared. So mass is constant. R is constant because we dealing with rigid rotor. And L sub z is just derivative over angle. So we again coming to really simple operator. Whew. So R times P angular momentum. If we are speaking about one Cartesian linear motion, then mass is a measure of inertia. The higher the mass, the like if a truck bumps into wall, will be destroyed. If a bicycle bumps into wall, bicycle will be destroyed because truck has larger inertia. So for rotational motion, there is an analog. So mass times radius will be a measure of inertia, and it is called momentum of inertia. Momentum of inertia, and it is often defined as mr squared. So if we define this measure of inertia with letter I mr squared, then functional form of Hamiltonian is the same. Something instead of angular momentum squared, something instead of momentum squared, angular momentum, and something instead of mass in the denominator. Right? And if we do a little practice of this minus I h bar, minus will come in the front, here will be h bar squared, two inertias, but it is specific inertia for rotation, right? And here it's second derivative over the angle. So if we compare with the smart shape of the Hamiltonian for free space that Alex was dictating, and I refused to accept, we will see the same functional form. The only difference that instead of coordinate it is angle, and instead of mass it is measure of inertia for rotational motion. Whew. So time is up. I do not want to borrow too much of your time. Let me just set up the plan. So we do have Hamiltonian. We reached the goal. But the next way is to diagonalize Hamiltonian, find eigenvalues, eigenvectors. So this course is a course in tricks. We never, or very rarely, solve problems directly. And one of the tricks here will be to show that Hamiltonian is proportional to LZ operator squared. An operator in power n and operator in power 1 always commute. Therefore, Hamiltonian will commute with both LZ squared and Hamiltonian will commute with LZ operator. But if two operators commute, their eigenvectors coincide. Therefore, instead of diagonalizing Hamiltonian, we will be diagonalizing LZ. Okay. And it will be really quick. Enough for today. Thanks so much for your energy, patience, and we will arrive to end of semester very soon.
It's just a long day.